Okay, so today we will discuss about the nanomaterials, and in the lectures on nanomaterials, I mainly focus on the characterization of the nanomaterials, which is the topic on today's lecture. So at first we are well aware about the nanomaterials. Okay, so in the past few lectures we have studied details about the what are nanomaterials and what is necessary for studying them. How can we apply these nanomaterials in our daily life, which helps in our uh, many necessities. Okay, so nanomaterials are the key components in the advancement of modern technology, covering a wide range of scientific fields. We have studied these, and these scientific fields include the environmental remediation, energy generation, storage devices, spintronics, and bioscience application. So, for these reasons, nanomaterials are very crucial or important nowadays. And the characterization of nanomaterials means simply the study of shape, size distribution, surface morphology, sorry, uh, surface morphology, surface morphology, and overall the atomic and molecular structure. Okay, so characterization of nanomaterials simply mean the study of shape, size distribution, surface morphology, and overall the atomic and molecular structures. The most important local probe method for the characterizing of nanomaterials are X-ray based techniques. X-ray based techniques. Now we have learned from the solid state physics that was present in our fifth semester that X-rays are used to study the different orientation of the planes of the crystal structure. So nanomaterials, in case of nanocrystals, we can also study the different orientation of the planes and the arrangement of the atoms with the help of this X-ray. Why? As because X-ray is an electromagnetic wave that has a comparable wavelength which is of the order of angstrom and which is comparable to the lattice spacing. We are well aware about that as because we have learned this in our fifth semester solid state physics. Okay, so we know that the X-rays are comparable to this lattice spacing which cause a diffraction phenomenon, and from this diffraction pattern we can study the structure and arrangement of the planes in the crystal. So nanocrystal can be studied with the help of X-ray based techniques. What involves this? It involves XRD. Now what is the meaning of XRD? X-ray diffraction. I am going to detail about it. So let us first just give the introduction. Sorry, diffraction. X-ray diffraction means XRD. Next thing is XPS. What is XPS? X-ray photo electron spectroscopy. Photo electron spectroscopy. And X-ray absorption phenomenon. X-ray absorption phenomenon. Different X-ray absorption technique. Okay, so these are some techniques which are based on X-ray and which are very much helpful in studying the nanocrystal structure. So these are based on the X-ray. Now there are another method are also present or also available for studying the nanomaterials or for the study of shape, size, surface morphology, etc., etc., which is based on the microscopy technique. Now this uh, microscopic microscopic technique. These microscopic techniques involves optical microscopy, optical microscopy to electron microscopy. These are main two classification of microscopy technique: optical microscopy and electron microscopy. What is the optical microscopy and what is the electron microscopy? We will going into detail about it. But at first I am going to give you the schematic classification. So this electron microscopy is very much important. Sorry, the color cannot be changed. Okay. Okay. Electron microscopy. Electron microscopy also involves different microscopical technique. Let us discuss them one by one. First, scanning electron microscopy. In short form, this is known as SIM. Next, transmission electron microscopy. In short, it is known as STEM. Next, scanning tunneling microscopy. STM in short. And there is also another technique also present, atomic force microscopy. Atomic force microscopy. In short, it is known as AF. So these are some microscopical technique based uh, sorry these are some microscopical technique available for the characterization of nanomaterials. Now let us discuss one by one them. Okay, so we will emphasize on the techniques. I will highlight them. Okay, so we will mainly discuss the techniques based on XRD. Okay, and all these things will be mentioned. But these two techniques are not present in our syllabus, but you can, if you are interested, then I will discuss it in later. But my main motive is to discuss the XRD and the microscopical technique used. There are also, it may be noted that there are also uh, bulk bulk sensitive probes, available, such as optical absorption spectroscopy, infrared spectroscopy, IR. Yes, Raman scattering are also used. Raman scattering also used in the characterization of nanomaterials. Okay, these are bulk sensitive probes. Okay, so I mainly classified different characterization techniques, which are first X-ray based technique, second one is microscopic technique, and the third one is bulk sensitive probe technique. Okay, so these are the three main classification of the characterization of the nanomaterials. So let us first discuss the X-ray based technique, which is XRD, is very important in this context. So without wasting any time, I am going to discuss the XRD. Let me choose, okay, blue color is, so X-ray diffraction technique. As I have already told you that X-rays are of comparable wavelength with that of the atomic spacing present in the crystal. So X-rays were used to study the uh, lattice plane and orientation of the lattice plane of the nanocrystals. What is X-ray? Scientist Ron Jane, in the year of 1901, got the Nobel Prize for the discovery of the X-rays. Now, when he first observed the X-ray, it was the emission of, sorry, it was the uh, emission of neutral uh, particle beam. Okay, so at first he were confused that it is gamma ray or X-ray. Later, when gamma ray was discovered, that it was known to be the nuclear phenomenon due to the nuclear excitation energy which converts to the gamma ray, and it gives the uh, it transforms the excited atom to normal atom with the emission of gamma radiation, excited nucleus to normal nucleus. So this is the nuclear phenomenon, but X-ray are not nuclear, this is atomic phenomenon. When atomic electron makes transition from higher energy state to lower energy state, X-rays are emitted. So X-rays are different from the gamma radiation, as because it was something new, it gave the as we know that the unknown quantity is designated as X in our algebra. So at first he were unknown about the new type of radiation, so he gave the name X-ray to this radiation. Okay, so this was the history behind the X-ray. Now let us discuss the X-ray diffraction. So X-ray diffraction, we have studied the solid state physics, that it is based upon the diffraction property, which is controlled by the Bragg's diffraction law. Bragg's law. What was the Bragg's law? Scientists Ewald and Lau were suggested that X-rays were electromagnetic waves, so it may have to establish it and correspond it for the diffraction property also. But the diffracting element were not available at that time. So scientists were very much gets curious about the diffracting element for the X-ray to cause the diffraction. So Lau suggested that the crystal planes can be considered to be the diffraction element for the X-rays, and it was successful. Lau was successful to get some uh, diffraction point, which later called the Lau diffraction pattern. So he was successful to obtain some diffraction points when he used the X-ray in the diffracting element caused by the lattice plane. But these diffracting element were different from the visible light diffraction element, as because he used the plane of diffraction rather than diffracting a single diffracting element. Okay, so if we consider the arrangement of lattice points like this, sorry, these are the lattice planes. So let us consider the X-ray on. Okay, so light ray falls on this atom and reflected back to this, and another light ray incident on the second atom placed in the second lattice plane and reflected back to this direction. Okay, so if I draw a normal, then this will be the incident angle and this will be the reflected angle, which is also theta. So okay, um, this angle will also be theta and this angle will also be theta. Now these two light rays will have some path difference. So to obtain the path difference, we have to draw two perpendicular on this. So if I name these as A point, this is B, this is C. So the relative path difference between the two light rays will be equal to some B. Okay, let me give this as B. BP plus BC, and this is the distance between two lattice point, which is equal to some D, the distance between two lattice plane. And um, theta means this is theta, theta means this is theta, and this is 90 degree. Okay, so this is 90 degree. Sorry. Okay, so this angle will be theta and this angle will be theta. So BP will be equal to BP will be equal to, due to this theta, BP will be d d sin theta, d sin theta from ABP triangle. Let me highlight it, ABP triangle. Similarly, from APC triangle, PC will be equal to d sin theta. This is theta, so this will be d sin theta, d sin theta. Okay, so that path difference become 2d sin theta. Now, according to the laws of diffraction, to get the maximum, principal maxima, the maxima, the path difference should be equal to some integral multiple of lambda. This is the condition for Bragg's law. Okay, so by X-ray diffraction we can get the orientation of the lattice planes and the structure of the lattice planes, as well as uh, if I know the wavelength of the light used, know the order of diffraction, know the diffracting angle, then we can determine easily the separation between two lattice plane. Okay, so this is the significance of the Bragg's law and X-ray diffraction. Now we become interested to study the image and look upon the image of the surfaces of the nanostructure material. So for the study of the nanostructure material, we have to apply some microscopical technique to magnify the nanomaterial, as because nanomaterials are very small, of the order of nanometer, so we have to magnify them. Okay, so for the magnification we at first use the optical microscopy. Optical microscopy. Now what is optical microscopy? Optical microscopy is a technique employed to closely view a sample through the magnification of the lens with visible light. Okay, let me write. Optical microscopy is the technique employed to closely view a sample through the magnification of a lens with visible light. There are two basic types of optical microscopy. First is simple microscope, and the second one is compound microscope. So in simple microscope we used a single lens or a series of lenses. Let me draw the principle. Okay, so uh, in simple microscope technique we use a single lens. If we use a single lens, and placed our eye in this, and the light rays will go along this, and if I place the object here, then the light ray will be this. Okay, I have drawn in opposite way. Okay, so the light ray will go along this and along this, and we get a magnified image in here. Okay, so the object was placed here, and we get the magnified image of the object here, which is erect and virtual image. This is the object, and this is the lens, this is the eye. Okay, okay, this is the principle of the simple microscope. Simple microscope, where we use a single lens or a set of lenses to enlarge an object through angular magnification, giving the viewer an erect, enlarged virtual image. The use of single convex lens or group of lenses are found in simple magnification devices such as magnifying glass. Okay, this principle is used in magnifying glass. So this is the method employed for the magnification of the nanostructure material. Another type of magnification is compound microscope technique. In this case, we used a series of lenses. Okay, series of lenses to enlarge an nanostructure material or object. So what we can do, compound microscope. Compound microscope. In this case, a lens is present near the object and another lens is present near our eye. The lens present near the object is known as the objective lens, and the lens present near the eye is called okay, the lens present near the object is known as objective, and the lens present near the eyes is called eyepiece. Eyepiece lens, and this is objective lens. Okay. Let me place an object here. Okay, so light rays will go along this, and sorry, this, and sorry, it's very difficult to draw in digital board, but I will try. This is the optic center. Okay, light rays not become not straight, but this should be straight line. Okay. So here we obtain an image which is known as the image 1. Image 1. This is the object. This image 1 corresponds to the objective lens. Now, the function of eyepiece is from this light ray will pass here and it will seem to coming from this, and this light ray will this and this. Okay, picture will be along this. So light rays will go from objective lens and form the image 1, and the light rays coming from the eyepiece lens will corresponds to an virtual image, virtual inverted image of the object in this site here. Here the enlarged enlarged inverted virtual image will be formed here. This is the image 2. So double image formed here. This is the magnified image produced by the compound microscope. This magnification is much more greater than this. So compound microscope is better than the simple microscope due to the presence of two uh, lenses, convex lenses. Okay, so these microscopical technique employed the visible light as the uh, working agent for the magnification, but nanomaterials are very small and it is hardly impossible, or it is not so fair for visualization of the nanomaterials. This technique is applicable up to the micron level, which is 10 to the power minus 6 order. Okay, of the order of 10 to the power minus 6, that is the micron order, optical optical microscope becomes very useful. But beyond that, small substances, that is of the order of 10 to the power minus 9, that is the nanomaterial, it is not so sufficient. So we have to change the magnified agent which cause a magnification to such a particle or such a element which can magnify much more better than that of the visible light. So after certain permutation, combination and trial and error method, scientists were uh, used the electron as the working agent for the magnification, and the microscopical technique were named as electron micros microscopy. So the problem was at first magnification cannot be achieved through optical microscope, mainly due to the wavelength of limitation due to the limitation in the wavelength of visible light. And the second one is the resolution becomes limited by aberration and diffraction method. These were the two problems on the optical microscopy. So the electron microscopy technique involves scanning electron microscopy, same, tunneling electron microscopy, transmission electron microscopy, same, scanning tunneling microscopy, STM, as well as AFM, etc. Okay. Now let us discuss another interesting thing here in this context, that is, we all know about the Louis de Broglie hypothesis, which relates the particle and wave nature of radiation. So from the optics we know that resolution is inversely proportional to the wavelength. Of light. Okay, and from de Broglie hypothesis we know that this is proportional to lambda is equal to some h by p, and this is equal to some root over of 2m into kinetic energy Ek. Okay, so when in case of electron, when it is acting at the potential difference of Vp, then the maximum kinetic energy Ek max will be equal to the EVP. Again, for electron is relativistic particle, total energy is equal c square p square plus m naught square c to the power 4 according to the theory of relativity, and E can be replaced as Ek plus m naught c square whole square c square p square plus m naught square c to the power 4 Ek square 2m naught c square Ek plus m naught square c to the power 4 is equal m c square p square plus m naught square c to the power 4, which gets cancelled out, and we get Ek plus 2m naught c square divided by c square is equal to p square. So from this we get lambda is equal to h by p, so lambda equal to h by 1 by c root over of Ek plus 2m naught c square is hc upon root over Ek plus m naught c square. This, by putting this value we get lambda is equal 2 3 divided by root Vp nanometer. If I replace dk in terms of EVP, then this will become established. Okay, and this is another relation for this. So again we know from de Broglie hypothesis that there are two properties of the quantum particle or radiation. One is particle property and another is wave property, but these two properties cannot be established simultaneously. At one event only one property dominates. This depends on the factor of the average distance d when become much greater than the wavelength of radiation or wavelength of the corresponding wave, then particle nature dominates. Particle nature dominates. But when d become comparable to the wavelength, wave nature dominates. So here, as d is much greater than the wavelength of electron's particle nature dominates. So in the electron microscopy technique, electron's particle nature dominates. So if you are asked to the basic principle of electron microscopy, you will say that the electron microscopy is based on the particle nature of electrons. Okay, so all the other properties will be discussed in another lecture. It is all about for today, where we have discussed the characterization of the nanomaterials. Thank you.